observe these interesting higher order processes, you have to achieve subradiance of 99.999%. In other words, it has to be quite perfect in order to see these transitions at all. But the encouraging thing is that while they're small, they're not too small for us to see. So we took advantage of the fact that in the molecule, the symmetry is perfect, so we can have completely subradiant or perfectly superradiant states. And then we looked for all of these transition moments separately. So this is the ground state of the molecule, which is always even, or gerade, the word that chemists prefer. This is the excited state, and we can make the excited state, and I mean electronically excited, as either odd or even. And so this way you can do the electric dipole transition, and between these states, we can see the higher order magnetic dipole or electric quadrupole transitions. And as you saw in this slide, some years ago, it was predicted that this forbidden magnetic dipole transition moment would scale as the bond length squared. And so we wanted to test this prediction. This is quite different fundamentally from the electric dipole transitions, which have no R scaling. So this will be quite unique, and we wanted to see that indeed this is the case. So we measured the transition strength of all these three transition types. So this is the E1. We normalized, this is different combinations of vibrational levels, the ones that we could access. So E1, we normalized one of them to unity, and then these are all relative to that unity. You can see indeed that these higher order processes are roughly suppressed by 10 to the 4, as the back of the envelope argument predicts. Unfortunately, here you cannot see directly this R squared dependence, because this is also, the pattern is also modulated by so-called Frank-Condon factors, so it just obscures the view. But the theoretical model that we used together with our colleagues contained all the physics, and if you look at the theoretical values, then indeed they actually lie flat on the measurements. So basically, this confirms that indeed these higher order radiation processes in bound molecules scale as the bond length squared as predicted. Now, so it was interesting to look at this forbidden transition strength, but also we wanted to make these subradiant, very long-lived states and just see what quenches them. So what limits their overall lifetime? Is it these radiation processes that are very weak, or something else might limit their lifetime? So in fact, these subradiant states were so long-lived that it was possible to coherently drive transitions between ground state molecules and these subradiant molecules, and see many cycles of Rabi oscillations. Here, only one cycle is shown. And by looking at the cycle, we could choose a pipe pulse that completely transfers population from ground state molecule to the subradiant molecule. And then, so this would be this first pulse in this scheme. And then we would wait and just let the subradiant molecule decay away. This is a variable wait time. And then we would just count how many were left after a certain time, basically. And you can see this nice exponential decay. And from the fitted lifetime, we could get by inverting the lifetime, we could get the natural line width. So the red traces, they show the Lorentzian line shapes that correspond to the measured line width. And they're for the 4 most weakly bound subradiant molecular states. So this is the closest to the threshold, and these are further and further from the threshold. Now, as an aside, since they are held in this Doppler-free regime, we should be able to see the lifetimes just by taking spectra directly, since we don't expect any broadening. And indeed, so the black points are just direct spectroscopy. And for the broader ones that are perhaps a kilohertz wide, they fall flat on top of each other. And then for the ones that are tens of hertz, they're actually, the direct measurements are broadened by the laser width because our laser is apparently not so great. But nonetheless, these red curves give you the actual correct true lifetimes. So this the experimental Q factor here exceeds 3 times 10 to the 12. Now, you might look at this and say something is suspicious because for the radiative processes, we predicted the decay rate to scale as bond length squared. Now the bond length grows toward the threshold, but somehow the width does not grow, but actually has the opposite trend. So the width increases away from the threshold, so that's unexpected, which means that it cannot be those higher order radiative processes that quench these subradiant states. It has to be something else. And it turned out that we also understand the process that quenches these long-lived subradiant states. It turned out that it's also a purely molecular process that does not exist for just unbound atomic systems. It's non-radiative decay, which chemists also know as pre-dissociation. So you can view this as follows. So this is our potential, interatomic potential for the particular atomic states. And so the blue is the wave function for one of these long-lived subradiant molecules. Now, you can think of it as a bound state, but it's not really a truly bound state because there are atomic states below. For example, there's the ground state, that would be way down here. That's too far, so that's actually not relevant here. But there is another fine structure state, and the bound wave function can, through short range interaction, can leak out into this continuum. So this is pre-dissociation. And we also were able to model this ultra-cold pre-dissociation, and you can see the results and how it agrees with the measurements. So in this plot, we show the natural line width that we've measured in units of hertz, so it goes from about 1 kilohertz to tens of hertz, versus the bond length, and we explored the range of bond lengths from about 40 to about 130 Bohr radii. Now, this is the boundary between superradiant and subradiant behavior. So this is 1 gamma exactly. Now, just for a check, we measured a couple of superradiant states, and indeed their line width is about a factor of 2 above this black line. As expected, superradiant states radiate at twice the rate. Now, as for the subradiant states, we were able to observe quite deep subradiance by a factor of about 300. So perhaps most subradiant that has been reported. And they follow this trend. Now, the red line would be the trend for the line widths if the width was limited by the higher order radiative processes. So this follows the R square trend. Clearly, we're not sensitive to this process in the lifetime measurements, but the blue line, as well as the red points, are the theoretical predictions of this non-radiative decay. So it seems to follow very, very well on the data. And just like we have this very nice asymptotic dependence that we measured for the transition strength of the magnetic dipole transition that scales as bond length squared, it turns out there's also a simple kind of asymptotic scaling of the non-radiative decay. And turns out that the non-radiative decay line width is proportional to the vibrational spacing. So as you get closer to the threshold, the level structure gets denser and denser, the spacing gets smaller, and the natural line width gets smaller. Since it's proportional to the vibrational spacing, one can actually rewrite it also asymptotically in terms of bond length. And so the dependence on the bond length R then depends, do we have 1 over R to the 6 type interaction or 1 over R to the 3 type long range interaction? And turns out that for this molecule, right around 80 Bohr, there's a transition, and we can directly see this transition from this van der Waals C6 over R6 to dipole-dipole C3 over R3. And it follows exactly the trend. All right. So Another interesting piece of asymptotic atom molecule physics is the anomalous magnetic behavior of these very long-range molecules when they're put in rather weak magnetic field. So we can think of them as anomalously large Zeeman shifts. For example, let's take just, again, strontium atoms, perhaps a mix of ground state and excited state atoms, and put them in a magnetic field and measure the magnetic shifts, the energy shifts in a field where the field ranges maybe within a few Gauss of 0. So because the excited state is triplet P1, we expect 3 Zeeman levels and quite linear Zeeman shifts with the expected G factor of 1.5. There's also a very weak quadratic contribution because of the other fine structure levels that are very far away. So the quadratic contribution, or this magnetic susceptibility chi, is very small, is a fraction of a Hertz per Gauss squared. Now, if we do the same thing, but take the same atoms, but bound them very weakly in very long-range molecules, the picture changes quite dramatically. And we see, actually, even you can see by eye the curving of the energy level. So there's a huge contribution to the quadratic shift. And in fact, the magnetic susceptibility is enhanced by a factor of 1 million, up to 1 million compared to unbound atoms. In fact, also here, the measurements are for a molecular state with a so-called omega quantum number of 0. So we actually expect 0 linear shifts as well. But in fact, the linear shifts, as you can see, were not 0. They were between 10 and 60% of the atomic linear shifts. So something is very unexpected, and the shifts are much larger than corresponding atomic case. And we can also plot the results. For example, this is this magnetic susceptibility, or the anomalously large quadratic shift. We can plot it as a function of the bond length, where, again, this is bond length in Bohr from about 100 on Bohr radii. And so there are several families of curves. You can kind of focus maybe just on the green one. And you can see that asymptotically, that also follows a very clean trend as the magnetic susceptibility is proportional to the bond length cubed. So one way to interpret this enormous increase in magnetic susceptibility is to think about the effect, a molecular effect called non-adiabatic Coriolis mixing. And I don't really have a good intuitive picture to give, except for me it's helpful to visualize this classical entity with 2 spheres on a spring that are both rotating and vibrating at the same time. And you can see that, I don't know if you can see that easily, but at the point of the cycle when the spring shrinks, the moment of inertia goes down and the rotation accelerates. And at the moment where the spring is extended, the moment of inertia is large and it slows down. So you can see directly a coupling between vibrational and rotational motion. So this is a classical example of Coriolis coupling, Coriolis mixing. And the same thing happens in molecules, except it's more complicated. And so in order to understand this Coriolis mixing, in our case, it's not so much rotation and vibration, but it's rotation and electronic angular momenta that couple. And so, again, if you look, these are the molecular potentials near the asymptote that we are studying. And there are 2 near this excited asymptote. One has omega 0, one omega 1. And the key is that they come very close to each other and they start to mix. Now, the very long range behavior is proportional to 1 over r cubed, where r again is the bond length. And so if you think about some kind of second order perturbation theory, the difference between the potentials, this very small value goes in the denominator, and then r cubed comes to the top. So you get something where magnetic susceptibility is proportional to r cubed. And because here we can make extremely large molecules that are 500 Bohr radii long, when you put in 500 Bohr here you get that factor of 1 million enhancement because it's an extremely long bond length. So again, the reason it's R cubed here is because our interatomic interaction goes as C3 over R to the third, and we can read that long-range behavior directly in the magnetic susceptibility. And I mentioned as well that there are also anomalous linear Zeeman shifts. And the very neat thing about our ability to precisely measure these anomalous linear shifts is we can actually directly read off from that this mixing angle. So I said there's Coriolis mixing, so you can represent a molecular wave function with some vibrational and rotational quantum numbers as a mixture of the two potential, omega 0 and omega 1. And the mixture can be parameterized as usual by some Coriolis mixing angle theta. And it turns out that these linear shifts allow us to directly measure theta. So we measured a bunch of these weakly bound levels, and for each we were able to pull out the angle, including amplitude and phase of the angle, so that here they're sort of represented on a unit circle. Before we did this, we didn't realize that you could actually look inside a molecular wave function and directly measure it. But turns out that you can do it here using these anomalous Zeeman shifts. So just to briefly summarize this point, we saw very large, very strongly enhanced magnetic susceptibility with the weakly bound molecules, and got to do a direct measurement of the molecular wave function. Okay, so just for the last bit, it's going to be more fun because fewer equations and more pictures. The last experiment that I want to describe is one we're working on right now, and this is ultracold photo-fragmentation. And this lends itself to some actual pretty pictures. So you can picture it as something like that. So again, we have, we want to study this asymptotic system. In other words, atom molecule behavior near the threshold, except now instead of studying weakly bound states, we want to learn about the asymptotic structure of the continuum. So we want to approach it from above. Photofragmentation you can think of as the simple reaction where you take a vibrating molecule and add a photon, and the photon has enough energy to not only excite the electronic degrees of freedom, but also impart extra energy to break the bond and send the fragments away with some well-defined velocity. So our molecule is very simple. It's just a diatomic, a linear diatomic molecule. So the fragmentation light has a linear polarization. So there are only two options. Depending on the type of the transition moment, either the molecule will be parallel to the polarization. So then in that case, the fragments will emerge vertically up and down, or the molecule will be perpendicular to the laser polarization, and then the fragments will emerge sort of sideways. And so here is a picture of fragmentation near our usual intercombination line threshold. So at this snapshot in time, you can see the fragments emerging pretty much up and down. So we can conclude that this is more or less a transition with a parallel moment. But something interesting emerges when we vary the energy that we impart to the fragments. So in this movie, this is not a movie in time. In other words, the time is fixed, but with each shot, we give more energy. So that's why the circles get larger. And you can see something very unexpected. At first, the fragments go up, and with higher energy, they start emerging sideways. So I don't know if you can see, but it's pretty clear. I'm just looking at the inner circle right now. You can ignore the outer circle. So here, again, up and down, and then at the end, they go sideways. So that's was very unexpected, because all we're changing is we're just giving the fragments a bit more energy. But now the whole pattern, the whole spatial pattern somehow changes. And we can quantify this by plotting it, the so-called anisotropy parameter. So usually this kind of spatial pattern is it can be parameterized by an angle theta, which is an argument to some Legendre polynomial. But basically, on this plot, the x-axis is the fragmentation energy. In other words, how much speed we give the fragments with the laser. And on the vertical axis is this anisotropy parameter. And this beta goes from 2. The value of 2 means it's a perfectly parallel transition, down to a value of -1, where -1 means it's a perfectly perpendicular transition. And when beta is 0, that would correspond to a perfectly symmetrical pattern, neither parallel nor perpendicular. And so for rotationless molecules, we have these red and blue points. The anisotropy parameter actually varies very strongly with energy. So something is happening for these, this is about 1 millikelvin of temperature here, so up to about 1 millikelvin of extra energy, the anisotropy strongly changes and then it settles down. And by the way, the same thing does not occur for molecules that start off with a little bit of rotation. But if you just focus on this curve, what we think what's happening there is that in the continuum, there are 2 potentials and one of them has a barrier. And so at some point, these fragments have to tunnel through a barrier at very low energies, but at the higher energies, they're all above the barrier. And so if we understand exactly how to fit this, we can basically directly extract these potential barrier from this kind of data. And perhaps for this particular asymptote, there's very good ab initio theory, so we kind of know what the barrier should look like. So perhaps we can just achieve good agreement between our experiment and what's expected. But this method can be applied very nicely to the asymptotes where we don't know theoretically what the barrier is. So for example, we can think about the doubly excited asymptote where where the molecule is near the threshold where both atoms are excited. And this is important also for many people who work with these divalent atoms because people want to make various quadrupolar quantum gases and they want to trap these particular long-lived states in traps. So their interactions are very important, but theoretically nothing is known about this continuum. But we can study it using the same technique. And this is more complicated. We get more complicated spatial patterns. And if you see it evolving with energy, again, there is some, as you increase the energy, the pattern goes from sideways to this clover leaf pattern. So something happens at some energy to make the fragments actually emerge in different directions. And because this is a more complicated pattern, it can, now it requires 2 anisotropy parameters that both vary with energy. And I have to say, we don't understand this fully yet, but hopefully this contains a lot of information about the interatomic interaction near threshold that cannot be seen with some other methods. And finally, this fragmentation has also application to precision measurements. So one thing we can do is we can take a molecule in its ground state in some vibrational level here and use a 2-photon fragmentation to get it back to the ground state continuum. And the reason that's nice is because both the initial and final states are a ground state, so the lifetimes are very long, and we expect a very, very narrow line width of this bound to continuum transition. And so this is a typical line width where we go from bound to the continuum. It has this arctan line shape, and the width of this line is about on the order of a kilohertz or a few kilohertz, which means that first of all, when we fragment, the fragments emerge with excess energy of much less than a microkelvin. So it's really ultra-cold photo-fragmentation, but also with such narrow bound to free line shapes, it's possible to measure the binding energies to a part in 10 to the 5 to a part in 10 to the 10, depending which energy we're talking about. And this ties in well with our goal of characterizing the van der Waals potential for the mass-dependent forces. Okay, and most importantly, I want to thank my team. This is my Columbia experimental team, maybe some of you know Jeff Iwata. He was one of your undergraduate students. He's very successful now at Columbia. Florian Appelbeck, Bart McGuire, Marco Tarallo, and Mickey McDonald. Also, I want to thank our collaborator, Robert Mashinsky from University of Warsaw, and his team of students who are outstanding quantum chemists, and they help us with the theoretical part of our work. Thanks for your attention.
Okay, thanks for the great talk. We have a couple of minutes for questions. There's one over there.
My question is like, with this photo-fragmentation, you showed like this.
I'm sorry. Oh.
The photo-fragmentation,
yes.
So like you have like two atoms, and then you showed us some pictures like there. I was wondering if you have like a double slit, so like two emitting points, and you see some interference fringes at that. And then the second question, like, is there? Do you see some entanglement between these two particles? Momentum.
Well, that's a good question. About I don't know about the 2 points. Yeah, you mean this here?
Like you start like with a 2-point source, like.
Yeah, it shouldn't be a 2-point source. It's a point source. It's a point source. If there's a 2-point source, I'm not sure. Yeah, I don't think there's a reason.
2-point sources for me like two atoms.
No. It would on this image at this resolution, it should definitely look like a 1-point source. Yeah, they should be. I think they should be entangled. By the time we see them, we can only take pictures of the atoms in their ground state. So we fragment them to one ground, one excited atom. And I think at that point, they're entangled. By the time we take a picture of them, the excited atom has decayed to the ground state, so then it's lost by then. So by the time we see it, they're not entangled, but I think initially for at least some number of microseconds, they would be. Yes?
There's a gradient state. Is it symmetric or anti-symmetric?
Well, so the ground state is symmetric. That means our subradiant state would also be symmetric. That means the dipole, electric dipole is forbidden.
For the other data that you show of photo-fragmentation, that was just like this still shot.
Mm-hmm.
It sort of looked like do you have any sense for, like, there's a little bit of asymmetry in the picture. It's just not this like perfect
Right.
symmetry. Do you have a sense for what might cause that kind of thing?
Well, there could be a little bit of overall tilt. If actual linear polarization of everything was a little bit off the axis of my slide, that's possible. But I don't know of any physical reason why sort of one ring would be asymmetric compared to the other ring or something like that. So yeah, I would expect them to be symmetric, and either it's an artifact or there's something else we don't understand.
Maybe I can ask one.
Sure.
Do you want to comment on is there prospect of using molecular detachment to produce exotic ultracold atoms?
Exotic, such as the ones that you cannot obtain by laser cooling alone. Yeah. Yes, that's another direction that we are hoping to pursue that I didn't put in this talk, is perhaps laser cooling a molecule that contains an atom that we are interested in but cannot obtain by laser cooling for technical reasons. So if we can get an ultra-cold molecule by laser cooling it directly, which is a very new method, and then photofragment it with extremely low energy, then we can obtain the desired atoms at an ultra-cold temperature. So yeah, so this will have an application in that direction as well.
In that case, thanks very much again.